delta x over delta t, I don't know how well you can see it in this figure here, is the slope of a straight line connecting these 2 points. And as the points come closer and closer, straight line will become tangent to the curve. The velocity at any part of the curve is a tangent to the curve at that point. Is tangent of that theta. This angle is theta, then delta x and over delta t by trigonometry is tan theta. Okay, once you can take one derivative, you can take any number of derivatives, and the derivative of the velocity is called the acceleration, and we write it as the second derivative of position. So I'm hoping you guys are comfortable with the notion of taking one or two or any number of derivatives. Interestingly, the first 2 derivatives have a name. First one is velocity, second one is acceleration. The third derivative, unfortunately, was never given a name. And I don't know why. I think the main reason is that there are no equations that involve the third derivative explicitly. F equals ma, the a is this fellow here, and nothing else is given an independent name. Of course, you can take a function and take derivatives any number of times. So you are supposed to know, for example, if x of t is t to the n, you are supposed to know dx dt is n to the t to the n minus 1. Then you're supposed to know derivatives of simple functions like sines and cosines. So if you don't know that, then, of course, you have to work harder than other people. If you know that, that may be enough for quite some time. Okay, so what I've said so far is a particle moving in time from point to point can be represented by a graph, x versus t. At any point on the graph, you can take the derivative, which will be tangent to the curve at each point, and its numerical value will be what you can call the instantaneous velocity at that point, and you can take the derivative of the derivative and call it the acceleration. So we are going to specialize to a very limited class of problems in the rest of this class. The limited class of problems is one in which the acceleration is just a constant. Now, that is not the most general thing, but I'm sure you guys have some idea why we are interested in that. So anybody know why that's such a big, so much time is spent on that? Yes? Pardon me?
Most problems involve gravity.
Right. The most famous example is that when things fall near the surface of the Earth, they all have the same acceleration. And the acceleration that's most common is called g, and that's 9.8 meters per second square. So that's a very typical problem. When you fall near the surface of the Earth, you are describing a problem of constant acceleration. That's why there's a lot of emphasis on sharpening your teeth by doing this class of problems. So the question we are going to ask is the following. If I tell you that the particle has a constant acceleration a, can you tell me what the position x is? Normally, I will give you a function and tell you to take any number of derivatives. That's very easy. This is the backwards problem. You're only given the particle as acceleration a, and you're asked to find out what is x. In other words, your job is to guess a function whose second derivative is a. And this is called integration, which is the opposite of differentiation. And integration is just guessing. Integration is not an algorithmic process like differentiation. If I give you a function, you know how to take the derivative. Change the independent variable, find the change in the function, take the ratio, and that's the derivative. The opposite is being asked here. I tell you something about the second derivative of a function and ask you what is the function. The way we do that is we guess. And the guessing has been going on for 300 years, so we sort of know how to guess. So let me think aloud and ask how I will guess in this problem. I will say, okay, this guy wants me to find a function which reduces to the number a when I take two derivatives. And I wrote somewhere here this result, which says that when I take a derivative, I lose a power of t. In the end, I don't want any powers of t. So it's very clear I got to start with a function that looks like t squared. This way, when I take two derivatives, there'll be no t left. But unfortunately, we know this is not the right answer, because if I take the first derivative, I get 2t. When I take the second derivative, I get 2. But I want to get a and not 2. Then it's very clear the way you patch that up is you multiply it by this constant, and now we are all set. This function will have the right second derivative. So this certainly describes a particle whose acceleration is a, where a is not dependent on time. But the question is this the most general answer, or is it just one answer? And I think you all know that this is not the most general answer. It is one answer. But I can add to this some number like 96. That'll still have the property that if you take two derivatives, you're going to get the same acceleration. So 96 now is a typical constant. So I'm going to give the name c, the constant. Everyone knows from calculus that if you're trying to find a function about which you know only the derivative, you can always add a constant to 1% answer without changing anything. But I think here you can do more. Right? You can add something else to the answer without invalidating it. And that is anything with 1 power of t in it. Because if you take one derivative, it will survive. But if you take two derivatives, it'll get wiped out. Now, it's not obvious, but it is true that you cannot add to this anymore. Basic idea in solving these equations, in integrating, is you find one answer so that when you take enough derivatives, the function does what it is supposed to do. But then, having found one answer, you can add to it anything that gets killed by the act of taking derivatives. If you're taking only one derivative, you can add a constant. If you're taking two derivatives, you can add a constant and something linear in t. If you knew only the third derivative of the function, you can add something quadratic in t without changing the outcome. So this is the most general position for a particle of constant acceleration, a. Now, you must remember that this describes a particle going side to side. I can also describe a particle going up and down. If I do that, I will like to call that coordinate y, then I will write the same thing. You've got to realize that in calculus, the symbols that you call x and y are completely arbitrary. If you know the second derivative of y to be a, then the answer looks like this. If you knew the second derivative of x, the answer looks like that. Now we have to ask, what are these numbers, b and c? So let me go back now to this expression. X of t equals at squared over 2 plus c plus bt. It is true, mathematically, you can add two numbers, but you've got to ask yourself, what am I doing as a physicist when I add these two numbers? What am I supposed to do with a and b? I mean, with this b and c? What value should I pick? The answer is that simply knowing the particle has that acceleration is not enough to tell you where the particle will be. For example, let's take the case where the particle is falling under gravity.